In this chapter, we're going to look at some more on forces, following on from what we did in the year one content on forces and mechanics. I wanted to start off just by recapping using vectors to represent forces. So here we've got two different forces, 3i plus 2j. We might write this in a column vector like this, so 3, 2 newtons. That means 3 newtons right and 2 newtons upwards. And then F2, 6i minus 4j. So that's 6 newtons to the right and then 4 newtons down. And they're both acting on a mass of 2 kilograms. And we've got to find the net force, or the total force, the acceleration, and then the direction and magnitude of the acceleration. So we can use F equals ma to help us, and we can just use our vectors in there. So the total force is going to be these two forces added together. So 3, 2 plus 6 minus 4 equals ma, so that's 2 times, I'll just leave it as a. So when I add these together, I'm going to get 9 minus 2 equals 2a, which then means the acceleration is going to be 4.5 minus 1. Okay, that's what the acceleration would be as a vector. So that means 4.5 to the right, and then minus 1, so 1 down. So overall, the object is going to accelerate in that direction. Okay. Now the net force as a vector, that would be this bit here. That's my total force, 9 minus 2, the two forces added together. The acceleration as a vector, that would be this bit here. And then the direction and magnitude, well, I've drawn my diagram here. The magnitude is going to be the length of this line here. So that'd be 4.5 squared plus 1 squared square rooted. Let's just see what that is. So it gives me about 4.61 meters per second squared. And the angle, I'm going to put the angle in there. So theta would be inverse tan of opposite over adjacent, so 1 over 4.5. So that's about 12.5 degrees. Now the way I would describe that is I'd say 12.5 degrees below the vector I, so below the horizontal. Okay. So that's just a reminder of how we can use vectors. And we're going to follow on from this with the year 2 content. We're going to really consider forces at angles, because that's essentially what vectors are. If we drew this out as a diagram, this problem, so there's my particle. We had one force which went 3 right and 2 up. So 3 right and 2 up, maybe it looks a bit like that. Okay, 3 right and 2 up. And then we had a different force. So I'm just going to do this in a different colour, which was 6 right and then 4 down. So 6 right and then 4 down. So we had another force that went like that. Okay, so 6 that way and 4 that way. That would be what this would look like as a diagram. And you can see that overall, I've got a stronger force down this way than I have that way. Hence why my force overall came out in this direction. So overall, my force was sort of like that. Okay, which you would expect from looking at the diagram. So we're going to look at a different way of analysing these forces, but not necessarily with vectors, but with the same sort of thinking. We're still going to consider the total horizontal and the total vertical forces. Okay, because you can see here that the total horizontal is going to be 6 plus 3, and the total vertical is going to be 2 and then minus 4. Okay. So here are some simpler diagrams. But here we're given, rather than a vector, we're given a magnitude and a direction. So this is kind of like doing it backwards. So I'm going to split these forces up as horizontal and vertical, which is basically splitting them into their I and J components. So the horizontal component here is going to be 9 cos 40. Okay, just think about your right angled triangle geometry. We've got sine, which is opposite over hypotenuse, cos, which is adjacent over hypotenuse. So the adjacent side to the angle, the side next to it basically, is going to be cos. Okay, the hypotenuse is 9. This is the adjacent. The vertical, which is opposite the angle, That's going to be 9 sine 40. Okay. So that's what's going to happen. We could work these out as decimals, but if we're doing calculations, it's probably easier to just leave them in an exact form like that. But 9 cos 40 is about 6.9, and 9 sine 40 is about 5.8. Okay, and then we could use these to analyze our system just by looking at vertical and horizontal forces, which we'll come on to later. This one here, part B. Again, let's do the vertical force first. So this vertical one here, so it's going downwards. So this is going to be, hypotenuse is 100. So that's 100 cos 18, because in this case, this side here is adjacent to my angle. This length here, this is going to be 100 sine 18. Okay, so it's not always just that, oh, horizontal is cos and vertical is sine. You have to consider where the angle is in your diagram. It's better to think about it as opposite the angle is sine, adjacent to the angle is cos. Okay, so it's all just to do with right angle triangle trigonometry for resolving the forces into vertical and horizontal components. If you've got two colours like I do, I would definitely suggest using that as well to help you. It tends to help students make it a bit clearer. Okay, so here's a bit more of a applied example. So a box of 8 kilograms lies on a smooth horizontal floor. A force of 10 newtons is applied at an angle of 30 degrees, causing the box to accelerate horizontally along the floor. Okay, so it's obviously going to accelerate to the right. Work out the acceleration of the box. Now, we've done questions like this before in year 1, but we've normally just had a horizontal force. We haven't really had to do with a force at an angle. What we would do normally is we would resolve the forces to the right. And we're still going to do that. It's just that we only want this component of the force here. Okay, just the horizontal bit. There's obviously a vertical bit as well, but we just want the horizontal bit for now. So this horizontal value here, the hypotenuse is 10, and this is adjacent to the angle, so this is going to be 10 cos 30 for that force there. The vertical force would be 10 sine 30. And we're then going to do the same approach, so we're going to resolve horizontally. So forces to the right would be 10 cos 30. It says it's smooth, it doesn't say there's any friction or anything like that. So we've just got 10 cos 30 equals ma, so that's 8 times a. And then I can type this into my calculator to solve it. So 10 cos 30 divided by 8. And I get 1.08 meters per second squared would be the acceleration. For part B, calculate the normal reaction between the box and the floor. So the normal reaction force, that is this floor here, this force here, that the floor is putting on the box. Okay. We should also consider the weight of the box if we're looking in that direction. So now, if we look at the forces vertically, we have got force R, which is upwards, which is what we're trying to find. But we've also got this force here upwards, 10 sine 30, so that's plus 10 sine 30, which is also pulling upwards. So if the force is going diagonally upwards here, then it goes right and upwards. So R plus 10 sine 30. Now we can either write equals 8g, because we can say that R plus this must be exactly the same as 8g to keep it balanced, because we're going to assume that the box is not lifting off the floor. Or we could have written R plus 10 sine 30 minus 8g, because the 8g is downwards, and then that equals m times the acceleration up and down, which is 0. Okay, I know it's accelerating to the right, but it's not accelerating up and down. And you can see that these two are just two ways of writing the same equation. And now we can solve this. So 8 times 9.8 minus 10 sine 30. we get 73.4 newtons. Okay, here's another example. So you've got two forces, P and Q, acting on an object. And we can see that P has got magnitude 10. So I'm just going to put this on there. And Q has got a magnitude of 8 newtons. Find the magnitude and direction of the resultant force. So basically, these are the two forces. Find out what's going to happen. So let's resolve P first of all. So that's got a force across and a force upwards. The vertical force here is going to be 10 sine 45 because it's opposite the 45. And the horizontal force is 10 cos 45 because it's adjacent to the 45. Now I'm going to resolve Q. That has also got a component which is this way, and it's got a component downwards. The horizontal component is going to be 8 cos 30 because it's adjacent to the 30, and the vertical component, which is opposite, is going to be 8 sine 30. Okay. Now we can resolve the forces. So if we just look at the horizontal forces first of all, we've got 10 cos 45 from force P plus 8 cos 30 from the force Q. We can then add those together. So we get about 14 newtons. If I now resolve vertically, so I'm going to choose up as being my positive direction, and I've got 10 sine 45 from force P, subtract 8 sine 30 from force Q, because one's going up and the other's going down, so one is positive and one is negative. So 10 sine 45 minus 8 sine 30, and we get 3.07. Okay, and that's positive 3.7 newtons, so that's going to be upwards. So overall, what's going to happen to this particle is my particle is going to go, it's got a force across of 14, and it's got a force upwards of 3.07. So overall, it's moving like that, diagonally to the right. Now to work out the magnitude of it, I could do 14 squared plus 3.07 squared square rooted, just to find the magnitude. So that's 14.33. So that's the magnitude of the force. And the angle, I'm going to put the angle in there. So that'd be inverse tan of opposite over adjacent. That's about 12.4 degrees. And I would write that as 12.4 degrees above I. Okay, because obviously this is my horizontal and it's above that. So that's a sort of problem that we're going to be doing quite a lot of, is resolving the forces into vertical components and horizontal components. And this is a skill that just comes up in almost every chapter of mechanics in year 2, really. Okay, here's another one. 3 forces act on a particle as shown. Given that the particle is in equilibrium, calculate the magnitude of P. So if it's in equilibrium, that means that the net force, okay, the overall force is 0. Basically, it is not going to accelerate in any given direction. So that means that the vertical forces must be 0, and it means that the horizontal forces must be 0. Okay, so it's not going to move up, down, or left or right. So let's do what we did before. Let's resolve the forces on the diagram. So we've got this one here, 140 at 45 degrees. So the vertical component here is going to be 140 sine 45. I always like to put arrows on these as well, just to show that it's going upwards, that component. And then we've got a horizontal component of 140 cos 45. Now let's resolve this other force, the 100. So it's got a vertical component of 100 sine 30. And it's got a horizontal component of 100 cos 30. And the last one, this P, we don't know what the value of P is, but we can still resolve it. It's got a force downwards of P sine theta. And it's got a force across of P cos theta. Okay. So now that we've got all our forces labelled on there, we can resolve them vertically and horizontally and find out what P is and what theta is. So let's look at the vertical forces first of all. Just move this out of the way. So remember we're saying the overall force is 0, so basically the forces are balanced in all directions. So looking vertically, I've got 140 sine 45 plus 100 sine 30, and it's plus because they're both pulling upwards. So that's plus 100 sine 30. Now we could either write minus p sine theta equals 0, because acceleration is 0, because it's in equilibrium, or we could just say that these two must be equal to p sine theta, because they are balanced. If we then look horizontally, so I'm going to go to the right, I've got 100 cos 30, so I'm doing this force here first, plus p cos theta, because they're both pulling to the right. They must be equal to this one, because the forces are balanced. That equals 140 cos 45. Or I could have written subtract 140 cos 45 equals 0, because it's not accelerating. So now it's just about solving these equations to find p and theta. Well, this top one here, if I work this out on my calculator, 140 sine 45 plus 100 sine 30. I'm just going to do it as a decimal, I think, for now. So that will tell me that p sine theta equals 149. If I solve this one for p cos theta, so I've got 140 cos 45 minus 100 cos 30. That tells me p cos theta is 12.39 or 12.4, I'm going to call it. Okay. Now we've solved equations that look like this before when we were doing when we did harmonic form in trig. And we ended up with r sine theta and r cos theta. And what we did to solve them was we drew a little triangle like this. We said this was theta and this was r, or in our case p, because then this is p sine theta, which is 149, and this is p cos theta, which is 12.4. So to work out p, I can just do Pythagoras of the two sides. So p is 149 squared plus 12.4 squared, square rooted. So it's going to be, well, not much bigger than 149, is it? So how about 149.5? Okay, then we could work out theta too. So we could do theta as inverse tan of 149 over 12.4. It's going to be quite a big angle, isn't it? It's going to be almost 90. 149 over 12.4, 85.2. Okay. So basically that is the force that P would need to be and the angle that P would need to be at to keep these other two forces in balance, so that overall the particle doesn't move anywhere and it's in equilibrium or doesn't accelerate in any direction. So the overall strategy in any of these questions is resolve any forces at angles into their two components, and then consider all of your forces horizontally and consider all of your forces vertically, taking into consideration their direction. So you should be able to have a go at exercise 5A now to practice this.